And we're back. Welcome back from the weekend. And today we will continue our discussion related to support vector machines. But today's module, the focus is on kernels. And so when we last left off, we talked about this idea of finding the right classifier. And in finding a linear hypothesis, there are many different choices you can make. And we talked about this idea of the best choice as being that particular linear hypothesis that was associated with the largest margin or gap between the positive examples and the negative examples. And so we came upon a constrained optimization problem, and we solved for the measurement of the margin. And this maximization, or finding the hyperplane that maximizes the margin, we posed as a minimization problem of 1/2 W transpose W. And then we had a number of constraints, these Yn times W transpose Xn plus B being greater than or equal to 1. And this particular constraint effectively says, get the classification correct. So find the maximum margin subject to getting the classification correct. And we have our weight vector W in D dimensions. So we took out this augmentation W0, and we took out that augmentation X0, and now we're just dealing with a linear hyperplane in the original input space or input feature vector representation. So W is from D-dimensional real value, and B is also a scalar on the real number line. Okay. So with that, we came up with Lagrangian formulation, and this was our Lagrangian, and we took our constraints and we turned them into equality constraints and then absorbed that greater than with our Lagrange variable alpha. And we have one of those such alphas associated with every input point from our in-sample points. And we called this expression the so-called slack. And so for points that are precisely on the margin, the slack is 0. For points that are off the margin, the slack is greater than 0. And so this primal problem is a minimization problem. And then we have a dual formulation, and we solve that dual formulation using the outcome of the solution to the primal problem. And so we minimize this primal form, or our Lagrangian, with respect to W and B. So we take the gradient with respect to W and gradient with respect to B, and we set them equal to 0, and we get these two expressions. W is the weighted sum, alpha n, Yn, Xn, and we also get this equality constraint, all the alpha n, Yn sum for each of the big N many class labels Yn and Lagrange variables alpha n. That weighted sum is equal to 0. And so we're going to apply this constraint to the dual optimization problem. We first solve for the gradient of the Lagrangian with respect to W and B, that minimization. And if we get that, we get these two solutions. We substitute them back into the Lagrangian. We're going to substitute that in here. We're going to substitute that in here. We're going to carry it later. And when we make the substitutions, we get this dual formulation. Now, this dual formulation is going to be a maximization problem. And we can turn that maximization to a minimization by negating it. And we do that because we want to use a quadratic programming solver in order to solve this. And so we have this maximization, and what that QP solver will give us is our vector of alphas. So our alpha here consists of alpha 1 associated with x1 up through and including alpha n associated with xn, or I should say more correctly, alpha big N. Okay. So in this dual optimization problem, we have that all of our alphas, the requirement is that they're at least 0. So alpha is greater than or equal to 0. And then also we carry forward that solution we had before as an equality constraint. And we use that in our dual maximization problem. And so this gives us, when we get the alphas, gives us a set of in-sample points xn for which the corresponding alphas are greater than 0. And these for which they're greater than 0, those are so-called support vectors. And so now our solution W for the hyperplane becomes a weighted sum over the support vectors, because if alpha n is 0 for the off-margin points, the interior points, those terms don't contribute to the definition of W. So we only sum together these weighted sums, alpha n, y, and xn, for the so-called support vectors. And then for a given value of the support vector, one of those xn's, for which alpha n is greater than 0, we then substitute in and solve this following equation to get a value for b. It doesn't matter which support vector you use. Okay. So this is where we left off, and today we're going to pick up with the so-called kernel trick. And so we had the dual formulation problem, and we notice in this example, this term, that's nothing more than an inner product. And it's an inner product between all of your in-sample points in d dimensions with all other in-sample points, including with itself. And so this inner product is used in forming the dual optimization problem, and we use the QP solver to find what our alpha vectors are for the appropriate minimization problem, because we take this dual, we negate it, and then we come up with a minimization problem. Now, we have this form, and this form here, we can actually take each one of these x's and perform a phi function transformation on it. So if I call phi on xn, that becomes zn, the corresponding representation of xn in feature space z. And likewise with xm, I can call phi on xm. That's zm. Now, if I do that, I can literally solve this same dual formulation problem, the support vector formulation, in feature space through this nonlinear mapping phi. And if I do that, well, this just becomes the equivalent problem here, where now it's in z space. And what does this do for us? Well, what it means is that now our dual formulation will find the max margin hyperplane in feature space. And so now we get the benefit of being able to draw highly nonlinear decision boundaries depending on the complexity of this transformation, our phi function. So with this, you can use the support vector machinery by computing the inner product in z space. But the interesting part is you don't have to visit that z space to get the benefit of that nonlinear decision boundary drawing afforded to you by the z space. So how is that? Well, if we did this, let's see what our final best hypothesis would be. So this is our g of x, our final best hypothesis, and instead of sine w transpose x, we have sine w transpose z, because of course that z is nothing more than the evaluation of our phi function, our transformation, our nonlinear transformation on x. Phi of x is equal to z. So we can actually compute sine of w transpose phi of x plus b. Now, of course, if we do this in z space, let's see what happens here. Well, if we know how to compute w, and we have our z here, that means we need this quantity, phi of x, that's nothing more than z. Okay, well, if we solve the support vector problem, we get our alphas, and these alphas now we can reconstruct w, get our expression for w, by taking all of those z vectors in feature space corresponding to a non-zero Lagrange multiplier alpha. All the alphas are non-zero. So we know how to calculate w here. And if this is how we calculate w, okay, that w, remember, exists or lives in feature space, because that's where we're solving this dual optimization problem if we convert that inner product in x space to an inner product in z space through that phi mapping. And so if we take our expression for w and we substitute that in here for w, well, what do we have? Well, we have this alpha n, y n, z n times z. So that would be the sum for all the support vectors. Zn is a support vector, and that would be alpha n, y n, z n transpose, because that w is transpose, with z. Okay. Now, of course, this z is the parameter, and we take that, add b. So here we have z transpose Zn transpose Z. And this requires our entire data set, right? It requires the entire data set because of this Zn term. So it's going to be the phi function evaluated on some of your data. So here, in order to compute this hypothesis, the output for our final best hypothesis on each one of our data points x, all we need is the ability to calculate the inner product Zn transpose Z. So this inner product in Z space is all we need in this framework. Okay, so let's take a look at B. Well, in similar fashion to the version of support vector machine in X space, we take a single support vector in feature space, and we then solve the following equation: ym w transpose zm plus b is equal to 1. Now, of course, if we make that substitution for w, well, what do we have? We have alpha n, y n, zn, and we have zm. So that becomes alpha, the summation, alpha n, yn, zn times zm. And of course, w is transpose, so we say zn transpose. Guess what? We have the inner product. So all we need in order to compute the SVM in feature space Z is this inner product defined in Z space. So you can use the same machinery by computing the inner product in Z space. And now this claim that I'll make is that you can compute the inner product in Z space without ever having gone into Z space, without ever having done this transformation of phi. And that's the so-called kernel trick, and we'll talk about that in great detail. Okay, so let's say we have two vectors in our input space x and x prime. They're from our x space, our original d-dimensional feature space representation, and we want to find the equivalent inner product in Z space. So certainly, if you compute your phi function on x, that's going to be Z transpose, so you transpose that result, times your phi function evaluated on x prime, that's your Z prime. So that gives us our Z transpose Z prime, which is the inner product in Z space. So let's define a function. And this function is called a kernel. And this kernel is going to operate on x and x prime in the original input space representation. And this kernel is going to compute the same value when it outputs it. That value, that k, evaluated on x and x prime, that value it computes is going to be the same value as if you transformed to Z space and did the inner product. And so this kernel is a function that returns the inner product of x and x prime in this Z space representation. So here's an example of a kernel. Let's say we have a two-dimensional input space representation, x, and we're going to use a second order phi function. Now, if we did this, of course, that Z space mapping is going to be an expansive mapping from 2 dimensions to 6 dimensions. So here we take an x vector is composed of the first feature x1 and the second feature x2. So if we had x prime, that would be x1 prime and x2 prime. So let's take a look at this phi function, the second order polynomial kernel function. It's nonlinear, and it goes from 2-dimensional mapping x to a 6-dimensional feature space representation Z. So what does it do? Okay, there's the first feature, x1, and then we say x1, x2. Okay, those are the first and second features. And then we say x1 squared, x2 squared, and then the cross term, x1, x2. Okay, so if we were to do the inner product in Z space for this phi function on original X space representation, what would that look like? Okay, well, if this is our corresponding Z, this mapping corresponding to X, so let's take Z and transpose with Z prime. So if that is Z, well, Z is 1, x1, x2, x1 squared, x2 squared, x1 times x2. that means z prime is going to be 1 x1 prime, x2 prime, x1 prime squared, x2 prime squared, x1 prime, x2 prime. Okay, so if we take the inner product between these two, what do we get? Well, multiply these two vectors together, the inner product, this transpose with the second one, and we get z transpose z prime is equal to 1. So that's the product of these two terms. We get x1 prime times x1. So x1 times x1 prime. We have x2 times x2 prime. There's that term. We have x1 squared times x1 prime squared. x1 squared, x1 prime squared. Okay. x2 squared times x2 prime squared. That's this term. And then lastly, we have x1, x2 times x1 prime, x2 prime. So we can just group together the first feature, the second feature. That gives us x1, x1 prime, x2, x2 prime. So there's our inner product. Okay. So we absolutely, this kernel function, through a polynomial expansion of degree 2, through this nonlinear mapping into z-space, computes the inner product in z-space. Now here, we've gone through the step of first doing the conversion to z-space, that phi function evaluation, so eval, okay, and then doing that inner product once we're in z-space, that product. Okay, so we can also compute that output k, because remember, this is just going to output a value. K is going to output some number, some scalar. Now, instead of doing that phi function transformation and then doing the inner product, we could actually compute this value directly. And let's take a look at how we might do this. Okay, so we can compute this kernel, k of xx prime, without doing the transformation, this phi function on this x and this x prime. We can do away with this transformation, but still get the same value as if we calculated this transformation and did the inner product in feature space. So let's consider the following function k on x and x prime. 1 plus x transpose x prime quantity squared. Now, if we look at what x transpose x prime is, that's just x1 prime plus x2 prime, right? We're just taking our x1, which is just x1, x2, and we're taking x1 prime, which is just our x1 prime, x2 prime. Okay, so we take the inner product between these two, we get 1, that was our leading 1, plus x1, x1 prime, plus x2, x2 prime, certainly within that parenthesized expression, quantity squared. Okay, so if we do this, let's expand this out, and we get this term squared, plus this term squared, plus this term squared, plus the cross terms, 2 times this term times this term. Okay, so let's look at this expression, all right? If we do this square, we just do it out. 1 plus x1 squared, x1 prime squared, so that's this term squared is 1. This term squared is x1 squared, x1 prime squared. This term squared, x2 squared, x2 prime squared. Okay, so now let's look at some of the cross terms. We have 2 times x1, x1 prime. Okay, that's one of our cross terms. We have 2 times x2, x2 prime. Okay, that's another cross term. And then we have 2 x1, x1 prime, x2, x2 prime. Okay, that's our other cross term. And that comes from, if we were to multiply 1 plus x1, x1 prime plus x2, x2 prime, we multiply that by itself, 1 plus x1, x1 prime plus x2, x2 prime. Well, we have all the square terms, all right? Let's look at the cross terms. So if we look at the cross terms here, we'd say first this times this times this times this, okay, plus this times this times this times this. Okay, that's another contribution. That's where you get the 2x1 x1 prime plus this times this. Well, that's another contribution. That's where you get this one, and then you have x2 x1 x1 prime x2 x2 prime x2 x2 prime x1 x1 prime. That's where you get two of these. That's where you get this last term. Okay, so if we look at this expression, we think about what this would be the result of for an inner product. You notice each term has a contribution from x and x prime. And so if we kind of isolate them, right, we have 1 times 1. Okay, that's like multiplying 1 times itself. Here, we have a contribution from x and a contribution from x prime. That's x1 squared, x prime squared. Here, x2 squared, x prime squared. So we can separate out the x1, the 1 here, that's the x1 squared, to separate out the x2 squared here. We separate out x1 squared, x1 here. We separate out x2 here. We separate out x1, x2. So x1, x2. Separate out those. And then the other contribution here, there's a 1. We have an x1 prime squared. Okay. We have an x2 prime squared. Okay. We have an x1 prime. Okay. We have x2 prime. And then we have an x1, x2, x1 prime, x2 prime. Okay. Now, the pesky thing about this is these coefficients here, 2. Something times itself is equal to 2. Well, that's nothing more than square root of 2. So we can include a square root of 2 here, a square root of 2 here, a square root of 2 on each of those terms in the prime version as well as in the non-prime version, square root of 2. So what does that look like? Well, this sum you would obtain if you took the inner product between these two vectors. This is the x version, and this is the x prime version. So we have 1 times 1, that's our 1. We have x1 squared, x1 prime squared, so write x1 squared here, x1 prime squared. Likewise, x2 squared, x2 prime squared. Square root of 2, radical 2, x1, radical 2, x1 prime. You multiply radical 2 times radical 2, you multiply these two terms, you get 2 x1, x1 prime, 2 x1, x1 prime. Same thing here, radical 2 times radical 2 is 2 x2, x2 prime. It's 2 x2, x2 prime. And then we have radical 2 here, that's 2 times x1, x1 prime, x2, x2 prime. And that's the last term. So this particular function, k of xx prime, for this form, is the same result as if we mapped through this polynomial degree 2 mapping into z-space. And here's our mapping. So our phi function gives us this mapping. If you evaluate phi on x, you get that vector. If you evaluate phi on x prime, you get that vector. So this kernel function returns the same value as if we use this phi function and then did the inner product in z-space. Okay. And so the interesting part is that we evaluate this kernel on an x space. We never do that phi function, but it returns the same value as if we had calculated this phi function and mapped to z-space. And this is the so-called kernel trick. You can compute the inner product in z-space, this particular z-space, without ever having to transform it into that z-space. And this is called kernel function, and this is called the kernel trick. Okay. And now, the interesting thing about this is if we think about that power here, this is called the polynomial kernel. And here's a polynomial kernel of degree 2. Now, we can generalize that to a polynomial kernel of arbitrary degree q. Now, if you think about this, well, in x space, when we compute the kernel value, well, what do we have here? This is in d dimensions. So we have d multiplications in order to compute this inner product. And then we take that result, add, that's trivial, and then we exponentiate to q, right? Each one of these we can do, d steps, and then we have one step for the addition, and then exponentiate, you can do that in one step. Now, certainly, if you took this d-dimensional vector, x transpose x prime, and you would actually multiply it out, we'd get the following. Feature by feature, x1, x1 prime, x2, x2 prime, plus xd, xd prime. Now, there are d many terms in here. Here are d terms. And now, if we exponentiate that to the q power, we're going to have a qth order polynomial. So we're going to have some power of q, x1 to the q power, x1 prime to the q power. And then we're going to have a lot of other terms leading from that, plus some scalar 1. Okay. So if we do this, we get a really large expansion, and the corresponding phi function that would give us this expansion, that would be a very large mapping into Z space. That would be very, very large, very high dimensionality for the corresponding phi function feature space mapping, which is the equivalent value of evaluating this polynomial expansion with this qth order or qth degree. So let's think about this. What would happen if you had a 10-dimensional input space representation, so d equals 10, and q, the degree for a polynomial expansion for this kernel, q is equal to 100. Well, you're going to have 100 terms at least. If you count the cross terms, that's a lot of terms. But if you compute it in input space representation with the kernel function, apply the kernel trick, well, that big calculation, multiplying all those high-dimensional terms with one another, and that's a very high complexity, that's just d multiplications and one other algorithmic step to do that exponentiation, right? So you have a huge savings, and in doing so, you can use support vector machines in this very high-dimensional Z space, but you only pay the cost, much smaller cost, of evaluation of this kernel function in effectively d plus 1 algorithmic steps. D steps for the multiplication, you add, we're not counting that, and then you exponentiate, that's another algorithmic step. You can also adjust the scale by just multiplying x transpose x prime by some scalar a, right, to change the way this constants and these coefficients work out. So q, if q is 100, it's a very simple operation in input space in this kernel. Same thing if q were 1,000. Now, if q is 1,000, oh my gosh, you'd have 1,000-order polynomial expansion in your phi function, and now you would have a much higher complexity to do the inner product between a vector that's at least 1,000 positions and another vector, these inner products. Okay, and so this kernel trick gives you the benefit of highly nonlinear feature spaces and thus highly nonlinear hyperplanes, but you don't pay the cost of evaluating this phi function in order to compute this inner product in the Z space. Okay, so you only need this kernel to be an inner product in some Z space, in some space Z. A kernel must exist, and that's the litmus test as to whether or not you can make use of the kernel. It just has to exist. You don't ever have to go to Z space. You can evaluate this inner product with the kernel trick and never have to visit Z space. And so in this example, we have the so-called radial basis kernel, radial basis kernel. And it's just a soft distance based on E. And we have this parameter lambda, which can kind of scale it up or scale it down. And this is our expression. We have x and x prime. It's certainly a function of x and x prime, so it is a kernel. Okay, it's the magnitude of the difference between x and x prime, and we have e to minus alpha or gamma of this magnitude. So let's look at a simple example. So if we evaluate this kernel, our radial basis kernel on x prime, well, it's just e And let's assume that this gamma is equal to 1, just for the simple example. We get this expression, right? We get e minus quantity, x minus x prime quantity squared. Okay, so if we take this squared term and we evaluate it, well, x minus x prime times x minus x prime, well, that's just x squared minus 2x x prime minus 2x x prime plus x prime squared. Okay, so we have a leading minus sign here on this expansion, because remember we said parenthesis minus, right? So it's minus the negation of that. So that gives us minus x squared minus x prime squared plus 2x x prime. Okay, and so now we have e raised to that power. That's nothing more, okay, if I have something added, it's just the product of e to each one of them. So that would be e to the minus x squared. We have e to the minus times e to the minus x prime squared times e to the 2x x prime. Okay, so if we write that out, we have e to the minus x squared, e to the minus x prime squared, and then we have this e to the 2x x prime. So if we do the Taylor series expansion of this, well, that's just you take that exponent and you raise it to the k power over k factorial, and you sum together for k goes from 0 to infinity. That's what e to the x is. It's in its Taylor series expansion. Okay, and I leave that to you to look up. So if we do that, this Taylor series expansion, okay, well, we can write the exponent k on each one separately. So we have 2 to the k, x to the k, x prime to the k, over k factorial, sum, k goes from 0 to infinity. Now, if we look at this, we can kind of group these together, the x version with the x prime version. And the x version of these terms, that's in blue, and the x prime version is in the red. And so here we have e to the minus x squared, that's x version. We have x to the k power, well, that's x version. And we have, for the x prime version, we have e to the minus x prime squared, okay, and we group that with x prime to the k power, okay. Now we have this pesky 2 to the k over k factorial. And what we can do with that is we can distribute this between the x variables and the x prime variables. How do we do that? We just write radical 2 to the k over radical k factorial. Okay, so now if we group that together, what do we get? We get the sum, k goes from 0 to infinity of, and it's important to remember that these leading e to the minus x squared, e to the minus x prime squared, those are constants underneath the summation. So I'm just going to put them back in just so I can group them together and show you. So we say radical 2 to the k over k factorial, k goes from 0 to infinity, of e to the minus x squared times x to the k power. We multiply this term, let me parenthesize that, by radical 2 to the k over k factorial e to the minus x prime squared x prime to the k power. And we group those together. And so this looks like an inner product, because it is an inner product. It's an inner product given vectors where k equals 0 is one feature in that vector, k equals 2, 1 is another term, k equals 3 is another term. So that's like taking the inner product between two vectors, one that has radical 2 to the 0 over 0 factorial e to the minus x squared x to the 0. And then you have another term here, that's for the k equals 0 term, radical 2 to the 0 over 0 factorial e to the minus x prime squared x prime to the 0 power. So this would be for k equals 0. We'd have another term for k equals 1. I won't write that out. Up to infinity, right? And so this result is exactly a kernel, and this result would be the resulting feature space if you had a phi function that transformed your input x into some z where z is of infinite dimension, right? Where z is in, if I were to write it this way, this is kind of an abusive notation, R infinity. And the particular transformation has each of these terms for k equals 0, k equals 1, k equals 2, so forth. This is the contribution from phi of x, each term, and this is the contribution for phi on x prime. Okay? All right. So this shows that this radial basis kernel, computed in X space representation, corresponds to an inner product in an infinite dimensional feature space Z. Okay. So if we did this with a mildly separable input space, what we could do, all right, well, here we have a target function that's in green, and we then sample randomly set of points in input space representation. So here we have the blue points that you could call the plus side of the line. We have these purple points, you could call that the minus side of the line. This green, that's the ground truth target function, and it's separating the plus side from the minus side. Now, using radial basis kernel, you get the following result. And the support vectors we find in Z space through the radial basis kernel, if we compute the inverse support vectors, we can identify them back in X input space. So this is a support vector, this is a support vector, this is a support vector, more correctly, a pre-image of the support vectors. So we have another support vector here. So we have 1, 2, 3, 4 support vectors on the plus side. We have 1, 2, 3, 4, 5 support vectors on the minus side. So we have 9 support vectors, and 9 images or pre-images of the support vectors. And so we can get our hyperplane mapped back into X space by literally sampling a bunch of points in X space and then testing them against our hyperplane in Z space and see when it goes from plus to minus and just draw those points where we get that transition point. And that's exactly what our black hyperplane is. We don't really know what it is, but we can figure it out by looking at when our class label transitions from +1 to -1. And you can do that by taking all kinds of X values, computing G of X once you get the best hypothesis through this phi function using the kernel. Okay, so this is what it would look like using this radial basis kernel. You start with a target function and you sample randomly 100 points all around feature space, and then you classify it with the radial basis kernel, solving the dual formulation. You get your alphas, compute your final best hypothesis G of X, and then you get your support vectors in Z space. You map them back to X space, pre-image, and this is what your solution looks like. Okay, so here is the quadratic programming coefficient matrix that we got as a result of the dual formulation. And so the QP solver solves this minimization problem, and it returns back your alphas. The only difference that the only difference or only change that we have when we use kernels with support vector machines, again, is all of these inner products. We're going to now use the kernel function in place of these inner products. We're going to run the kernel function on these x and xi and xj's. And so this corresponds to a new coefficient matrix that we feed into our quadratic programming solver, or QP solver, and it'll give us the alphas as usual. So this is the only difference, and you can construct this from the data set along with the definition of what your kernel function is. And because we use the kernel trick, we get the benefit of a highly nonlinear feature space and therefore highly nonlinear decision boundaries and hypotheses, but we don't pay the cost of transforming to z-space and doing the inner product in z-space. Okay, and so this is our result. And once we get our final SVM hypothesis using the kernel, well, we know what our kernel function is. We identify our support vectors, and with our support vectors in z-space, we can compute what our final best hypothesis W is, and then we take our definition of what our final best hypothesis is for that W, and we substitute in what this W is, and this gives us a set of inner products, a kernel function evaluated across the entire data set, given that input parameter X. We can solve for B by taking one of the support vectors in z-space and solving this equation. And again, this just involves an evaluation of the kernel function, our inner product, across our data set. For that particular XM is that support vector corresponding to alpha M, where alpha M is greater than 0. Right? That means XM is a support vector. Right? So to solve for B, you take a support vector and you solve that constraint problem, and it gives you the value of B. Now, this all depends on our data set. This quantity, that depends on the data set. Because here we have, for all the support vectors, we have the kernel evaluated on a corresponding support vector with that input parameter. And likewise for B, we do the same thing. And so this kernel is all we need. Along with our W, we can take the kernel and use that in everything we need to get this kernelized support vector machine. Okay, so how do we know that this Z really exists? Well, we want to know if this kernel evaluation is a so-called valid kernel. And there are multiple ways to do this, and we will pick back up next time with how you might do this in designing your own kernel. Okay, so with that, we will meet back up on Thursday. I will see you all on Thursday.